everyone and welcome to Twashta. In this video, we are going to discuss this question that appeared in CSIR NET December 2018 paper. The question is from section C and it says, for a reversible non-competitive inhibition of an enzyme, choose the plot that you would use to determine Km. I will start with a brief introduction of double reciprocal plot or Lineweaver-Burke plot and go on to discussing about various types of inhibition. This is the famous Michaelis-Menten plot which describes the relationship between substrate concentration and initial velocity of an enzyme catalyzed reaction. And it is algebraically represented by the Michaelis-Menten equation. I have talked about this graph in one of the previous videos, so I will not go into the details. If you want a quick recap, then you can watch that video first using the link mentioned in the description. Now, the problem with this graph is that Vmax is calculated by extrapolating the plot because V0 infinitely approaches but never reaches Vmax. And this gives only an approximate value of Vmax. For a more accurate determination of Vmax, Michaelis-Menten equation is transformed into another equation called the Lineweaver-Burke equation. First transformation is performed by simply taking the reciprocal of both the sides of the Michaelis-Menten equation. Next, the right-hand side components are separated and the equation is simplified further to finally give the Lineweaver-Burke equation. Notice that this equation resembles the equation for a straight line plot. Therefore, a plot between reciprocal of initial velocity V0 and reciprocal of substrate competition, and hence the name double reciprocal plot, yields a straight line. The line has a slope equal to Km by Vmax with 1 by Vmax as y-axis intercept. So from here Vmax can be more accurately determined and minus 1 by Km is the x-axis intercept. Now, enzymes can be subjected to inhibition by molecular agents called enzyme inhibitors. Enzyme inhibitors interfere with catalysis and they either slow down or completely stop the enzymatic reaction. They can be broadly of two types, reversible or irreversible. Irreversible inhibitors irreversibly disrupts the functionality of the enzyme by either covalently binding to the enzyme or destroying the functional group at the active site. While reversible inhibitors binds to the enzyme in a reversible manner, and that is why it affects the kinetics of the enzyme. There are three main types of reversible inhibition: competitive, uncompetitive, and mixed. As the name itself suggests, a competitive inhibitor competes with the substrate for the same binding site of the enzyme. They usually resemble the substrate and combine with the enzyme to form an enzyme inhibitor complex, but without forming the required product. An uncompetitive inhibitor, on the other hand, binds to a site different from the substrate binding site. But unlike competitive inhibitor, uncompetitive inhibitor binds only to enzyme substrate complex. Lastly, there is mixed inhibition. It is called mixed because mixed inhibitors can bind either to free enzyme as in competitive inhibition or to enzyme substrate complex as in uncompetitive inhibition. But mixed inhibitor binds only at a site different from the substrate binding site. The Lineweaver-Burke plot or the double reciprocal plot can be easily used to determine whether an enzyme inhibitor is competitive, uncompetitive, or mixed. In case of competitive inhibition, there is inhibitor and there is substrate, and they both are competing to bind to the same binding site, right? And depending upon the relative proportion of the two, some of the enzyme will bind to the inhibitor and some will bind to the substrate. In the absence of the inhibitor, the total enzyme was available to the substrate alone. But in the presence of inhibitor, the amount of enzyme available to the substrate will decrease because some amount of the enzyme will bind to the inhibitor, right? But because the inhibitor binds reversibly to the enzyme, increasing the substrate concentration will increase the probability of substrate binding to the enzyme. And that is why Km will increase in this case. Note that Vmax will not change because the same Vmax can still be achieved by increasing the substrate concentration by enormous amounts. So the Km will increase by a factor alpha, and the Michaelis-Menten equation also changes accordingly, with alpha Km replacing the Km term. Here alpha is equal to 1 plus concentration of inhibitor upon Ki, and Ki is the equilibrium constant of inhibitor binding. The double reciprocal plot that we obtain for competitive inhibition looks like this. Vmax remains same, so all the lines intersect at y-axis, and Km increases with increase in inhibitor concentration. Now, in case of uncompetitive inhibition, where the inhibitor binds to enzyme substrate complex, Vmax will increase. Why? Because inhibitor is binding to the enzyme substrate complex, and that too at a different site. So no matter how much substrate is present, inhibitor will still inhibit the reaction as it binds after the substrate is bound to the enzyme. So the maximum velocity will never be the same. It will decrease by a factor alpha dash. And since Vmax is decreasing, less amount of substrate will be required to reach that decreased Vmax. And so Km will also decrease by factor alpha dash. The Michaelis-Menten equation will also change accordingly, and the double reciprocal plot for uncompetitive inhibition will look like this. Km and Vmax both are decreasing with increase in inhibitor concentration, and this gives us a set of parallel lines. So parallel lines means uncompetitive inhibition, just to remember for the sake of exams. Then we have mixed inhibition, where inhibitor can bind to either free enzyme or to the enzyme substrate complex, and at a different site, of course. This is mixed because when the inhibitor will bind to free enzyme, the enzyme kinetics of competitive inhibition will be followed, and when the inhibitor will bind to the enzyme substrate complex, then the kinetics of uncompetitive inhibition will be followed. So both Km and Vmax are affected. The apparent Km will become alpha Km by alpha dash. That's because Km increases by a factor of alpha in competitive inhibition and decreases by a factor of alpha dash in uncompetitive inhibition. So combining both, we arrive at this relation. Similarly, Vmax will decrease by a factor of alpha dash as in uncompetitive inhibition. The double reciprocal plot for mixed inhibition will look like this. Now, this is the case when alpha is greater than alpha dash. Km is increasing and Vmax is decreasing with increase in inhibitor concentration. Now, I want you to pause the video here and figure out how the graph will look when alpha dash will be greater than alpha. with alpha dash greater than alpha, the Km will decrease. So the graph will look something like this, with both Km and Vmax decreasing with increase in inhibitor concentration. There is a special case of mixed inhibition when alpha will be equal to alpha dash, and this is called non-competitive inhibition. In this case, Km will remain unchanged because alpha and alpha dash will cancel out, and Vmax will decrease by factor alpha dash. So the graph will look something like this. Only Vmax decreases and Km remains the same with increase in inhibitor concentration. With this, we have come to an end of this discussion, and now let us return back to our question. For a reversible non-competitive inhibition of an enzyme, choose the plot that you would use to determine Km. And now we all know for sure that the answer would be the plot in the third option. I hope you found our explanation helpful. If you have a question that deserves a video explanation, please let us know in the comments. Thank you.